So let's start off this section by just saying that different materials need different amounts of heat to change their temperature by 1 degree Celsius. So my examples, we're going to have copper and water, and we'll have both of them be 1 kilogram. And if we wanted to increase their temperature both by 1 degree Celsius, you would have to give the water 4,186 joules, but copper would only need 440 joules. So this idea gets given the name of specific heat. So like we could say the specific heat of copper would be 440 joules for 1 kilogram and for 1 degree Celsius. So this is what we call the specific heat of a material. And it depends on what material you're working with. So if you need the value for a certain material, you just look it up in a table. Like you can just use an online table if you like. If it's a quiz or a test or something, I would give it to you in the problem itself. But all of these values would only tell you the heat needed to raise the temperature of 1 kilogram by 1 degree Celsius. But what if you had a different mass? Or what if you wanted a different temperature change? So this is the value from the table that you would plug in. But then if you had maybe a chunk of copper that was 3.6 kilograms and you wanted to raise its temperature by 5 degrees. Well, to find out how much heat you would need to do that, you plug in that total amount of mass of copper that you have and the 5 degrees of temperature change that you want, and you'll get the needed heat. If you want to use the shorthand version of it, here you go. Your book uses capital H for heat, little m for mass, lowercase c for specific heat, and delta T, this little triangle is a delta, and it just means change in. So this delta T is change in temperature. So you might just plug in 5 degrees there. We don't just have a T there because then you might accidentally plug in the temperature of the material itself, not the temperature change that you're going for. All right, now we do latent heat. And for now, let's just call that phase change heat. So the amount of heat that you would need to change a material from a solid to a liquid, or a liquid to a gas, or a gas back to a liquid. Right? There's going to be heat involved in those changes. Whenever you're doing a phase change, you need extra energy just to do the melting or just to do the boiling. That takes its own energy. And of course, if you were going to be doing the reverse of that, instead of melting, you were freezing, or instead of boiling, you were condensing, you would have to be taking that energy away from the material. And while this is happening, while your heat is going into latent heat, while your heat is changing the phase, the energy that you're putting in doesn't change the temperature, because all of the energy is going from changing like the water into water vapor and boiling it. So latent heat is often nicknamed hidden heat because you don't see its effect on a thermometer. And if you quick need a mental picture for condensing, just imagine a cold glass of ice water in the summer. And then you get that condensation on the outside of your glass. And that's just the water vapor in the air. And the water vapor in the air touches the side of your cold cup. And then the water vapor in the air got cold enough that it changes from being a vapor that we can't see, and it turns into a droplet onto the side of your cup. All right, so here's just a kind of a quick visual to this. So once I press play, the ice in the cup, right? So right now we have water ice in the cup. And once I press play, imagine that the heat is just being continuously added to this. And up here, the graph, we're going to start off down here at a cold temperature for ice. And then the heat will just be constantly added. And then we'll be seeing that the temperature increases in kind of these stepwise fashions. Right? So adding heat to the ice, notice the temperature is changing. All right, they're still adding heat, but the temperature is still 0. Still adding heat, but the temperature is 0. All the energy that is being added as heat is only going to melting the ice, to breaking those bonds apart. Now to this liquid, you can see that it's heating up again. You notice some of it is evaporating. The evaporation will happen faster and faster and faster as the temperature gets higher, but it's not technically boiling yet. Once you get those water vapor bubbles forming actually in the pot, that's boiling. And so now it's still adding heat to the water pot, but notice the temperature is not going up any higher. It's just evaporating. And we can figure out how much heat it takes to do those phase changes. That has to go into that latent hidden heat. Again, with some more tables and equations, and we'll do some examples later. So first we're only going to focus on melting or freezing. So ignore boiling right now and ignore condensing. We're just doing melting and freezing. So the amount of latent heat that it would take to melt or freeze a material, again, depends on the type of material. So that's why we need a table. And before we would look up the specific heat, that was our constant for that material, and we would plug it into the equation. Here our constant, instead of calling it the specific heat, here we call it the latent heat of fusion. But really, it's just a constant for a certain type of material that you plug in. So if you want to know how much heat, how much energy you would need to do the melting or freezing, you need to know how much mass you have, and you need to know what material it is. So you can look up this constant and plug it in. And it's the same thing with boiling or condensing, but you have to look up a different constant. So to boil or condense, to figure out how much heat must be added, and that's for boiling. But if you're going to be condensing a gas into a liquid, you have to be removing the energy. But you can still figure out the amount of that with the same equation. Right? The constant that you're going to look up is called the latent heat of vaporization. But it's just a confusing name for the amount of energy that it takes to boil 1 kilogram of a certain material. And so you have to know what material it is and plug it in from a table. A couple of tidbits just to cover real quick. If the air pressure is higher, like in a pressure cooker, the boiling temperature increases. So one reason why you use a pressure cooker is to make the air pressure higher, to raise the boiling temperature. So you can actually get your spaghetti or whatever you're putting in there to be higher than 100 degrees Celsius. And then your food will cook faster. And it's also worth noting that water doesn't have to be at the boiling point to evaporate. Right? Evaporation can happen below the boiling point as long as the air isn't already at 100% relative humidity. And I'm pretty sure you would know a really humid day when you felt one, right? On those days, those really humid days, it's harder to evaporate your sweat. On really humid days, you can't have evaporation unless you get the temperature up to the boiling point. At the boiling point, you can force the evaporation. You can force it to become a gas.